There we go. All right, in this video we're talking about standing waves. Not bad, not bad. You kind of see it going. Standing waves. All right, what is a standing wave? Welcome back, ladies and gentlemen. Essentially, a standing wave is a wave that it looks like it's standing still, hence the name standing. And what we observe, what we seem to see, is something like this. Almost like I was just doing, where it's twirling around, but it doesn't have to be twirling around. It's still a vibration. It's still a displacement from equilibrium. And so we got this action up and down going on. And it's weird though, because the crest seems to not go anywhere. Where if you just shake one end of something, it seems like that's a terrible example. You get rid of that string. You know, you do one of these things, and it seems like the crest travels somewhere. The wave travels, but the medium does not. Well, here the wave seems to remain stationary. That's weird. What's really going on is the standing wave comes about from something called superposition, or more specifically, constructive interference. You get a wave traveling one direction down the length of the string. What's going to happen is that this end over here is fixed, and the wave will actually reflect. It reflects off of that end and comes back. And if you get things just right, the reflected wave and the wave coming in, the incident wave, those two waves, superimpose, they overlap on top of each other, and they build this thing, and it is timed just so it looks like it's staying there. So here's a couple things that are important about this. We're gonna refer to some things here. There's a length. They're there. All right. And here's what we know from this image right here. Okay, you can clearly see that there's a node here, and at the node there's no displacement, and then there's maximum displacement, so there's an antinode, and then back to a node where there's no displacement. Well, for one complete cycle, we would need a trough and then a crest, but we're missing this half. So this represents half of a wavelength. This length is equal to 1/2 the wavelength of that wave. So that's kind of cool and interesting. Now, what we say about this, and I can show this pretty handily. I can say, well, just look over here. If I watch a wave, it kind of typically does one of those, right? And this would be the length of one wave from there to there. But what I see here is just one crest. You might think you also see a trough, and you do, but this trough is not a trough of that wave. This trough is a trough of a different wave. They have to be offset from each other. So what we're really looking at is this distance there. This distance is that. Because for this crest right here, the trough would have to be over here somewhere, and we simply don't see that. So here's our length, and there's our wavelength, and therefore length is 1/2 of the wavelength. And this has a name right here. This particular style has a name. It's often called the first harmonic. If you're into music, you start to understand what's going on with this stuff. This might also be called, there's some names you want to be familiar with, the fundamental harmonic, or some fundamental harmonic, fundamental mode, or sometimes the fundamental frequency. So those terms would be interchangeable. And it's the fundamental because it's the greatest wavelength possible for this given length of string. You cannot create a standing wave on this string that would have a wavelength any larger than this particular wavelength. It would not be possible. You can get smaller, you'll see that, but it would not be possible to get larger. So let's investigate a little bit further into what's going on here. Okay, so if we have our length set, we have a length of string, right? And we might see this, where there is a node, there is an antinode, and there is another node. Okay, just recognizing a few parts. And instead of that, we might see something else on the same length of string. We might see where it comes up, does this, and then down and does that. But for the standing wave, this wave might have been sent that way, bounced off of that fixed point, and reflected back. And we see a standing wave like this. Okay, so here we see a node, we see an antinode. There's a node in the middle now. We see an antinode there and a final node there. And there's really just about an infinite number of possibilities here. Okay, for the same length, we might see this, and then this. And notice what's going on. Both ends have to be fixed. Both ends of that string are fixed and cannot oscillate. It can only oscillate where it's loose in the middle. And that's exactly what we're talking about here. Nodes are where it's fixed or does not oscillate. And there's antinode, and there's node, and antinode, and node, and antinode, and node. Okay. But, got to complete the standing wave here. Its reflection would look like that. Okay, well, there clearly are differences going on. Let's say we have the same length in all three of these examples. So we have from there to there is our length L. Okay. So let's look at these. This first one we recognize is the first or fundamental harmonic. And so here's the deal. We have a wavelength, and now these waves are traveling up and down the string, back and forth, and because the speed of the wave depends on the medium, the speeds are the same in all three of these examples. And you can change the speed by changing the tension or the mass per unit length of that string. But let's say it's the same string in all three cases. Under the same tension, those factors would be the same. You'd have the same speed. And so we're going to come back to this very important relationship about the speed of a wave and the wavelength and the frequency that's taking place here. Well, here in this first fundamental harmonic, okay, we typically will call that or symbolize that with just F1, frequency 1 for the first harmonic. Here, this is going to be the second. This is the next possible wavelength where we see the L equal to, well, it looks like a crest and a trough and one complete cycle. So here we see that L is equal to wavelength. Whereas here we saw L is equal to 1/2 wavelength, right? And down here, check this out. Let's see, up and down, there's one complete cycle plus half. So L is equal to 3/2 of a wavelength. Okay, well then, and there's no other possible combination in between these two. This is the next one. This is your second harmonic frequency. And you just designate it F2. This would be your third harmonic frequency. Designate F3. Easy enough, okay? And it could keep going, right? So what we want to do is we want to have a sort of general thing to say, but there's some specifics we want to have with these different harmonics. So check this out. From that relationship, this relationship between speed, wavelength, and frequency is going to guide us this whole way. From that relationship, we can relate length to wavelength, and therefore we can define certain lengths that produce these harmonic frequencies. Think of this. When wavelength equals twice the length of the string, and that's what we have here. Wavelength is twice that value, right? Then that frequency that produces that situation is equal to the speed of the wave divided by the wavelength. But the wavelength is equal to twice the length of the string. So I'm just doing a substitution right there to there. That's the only thing different. And this is kind of cool. So I've got, all right, this basic thing right here. Can't simplify that anymore. Well, how about when the wavelength is equal to L? So that's this situation right here, right? And that's going to be the second. Oh, I'm sorry, I forgot the one designation right there. And this is wavelength of that first harmonic. Sorry about that. Well, we got the second harmonic. The speed is the same. And so there's that. But substitution time, so it's equal to that. What is this equal to? There's something I can say about this second harmonic frequency relative to the first harmonic frequency. Okay, so this right here, come on marker, there we go, is equal to twice the first harmonic. Because if I multiply that by 2, then the 2 cancels and I get that. There we go. How about when the wavelength equals, well, what was the third harmonic? What do we say here? It's equal to 3/2 of the wavelength. L is 3/2 of the wavelength. So wavelength is 2/3 of the length of the string. 2/3 of the length. This third harmonic frequency is going to be velocity divided by this third wavelength. And so velocity divided by the 2/3 L. And I can simplify that. It's going to be 3/2 velocity divided by L. And so look at this. Here I have 1/2 V over L. Here's 3/2 V over L. So this is equivalent to 3 times that, or 3 times the fundamental frequency. The third harmonic is equal to 3 times the fundamental harmonic. Okay. And so let's say something generally. We can say that any harmonic frequency is equal to that value of n multiplied by the fundamental frequency, which really comes down to that value n multiplied by v over 2L, whatever the length of the string is. And assuming we're talking about different wavelengths and frequencies on the same string, right? Of course, because v has to be a constant value for figuring out these frequencies on a given string. So this works for what values of n? For n equals well, 1, 2, 3, and so on. No problem. This is kind of important. Harmonic frequencies on a string. You can figure out any harmonic frequency you wanted if you knew either the fundamental harmonic or if you knew some information about the physical situation going on. Cool stuff. Okay. But check this out. Strings aren't the only things that vibrate. Oh, this is going to get interesting. And but you'll see it's going to be in some ways very much like strings. How does your wind section in an orchestra work? Well, they get air vibrating. How do the brass section work? How do the percussion things work? Well, ultimately, you're getting air vibrating. Even though there may be a membrane or a reed or your lips on the horn or on the trumpet, ultimately you're getting a column of air vibrating. Same thing with like a pipe organ. So we're looking at vibrating air columns. All right, and we're going to draw this out. This is going to be pretty basic here. Column of air, maybe in a tube or something like that, part of an instrument. But I'm going to specify something that does matter. The one end will be open, and one end will be closed. So imagine, blowing over the top of a soda bottle and getting it to the kind of sound. Well, you have a closed end and an open end, and you get the air inside vibrating to make a note. Well, here we go. We have, let me use a different color here. This is kind of neat. From here to here, that looks like a length. That is the length of the column of air. All right, and here's the deal. At the closed end, this is where you see a node. If you were to track density of the air that's vibrating, you create a standing wave here, and this is a node. And what you have where it's open, if you look at the density of the air for the standing wave, there's a node there. You get an antinode at the open end. And it simply is that way. It always will be. Where it's closed, you get the node. Where it's open, you get an antinode. Okay, well, check this out. We have a relationship between wavelength, turn this sideways, you see part of a wave, and length of that column of air, or height if you prefer, doesn't matter. So we can say that in this case, this looks like from the center location up to a crest, and so this would be actually half, no, not half, a quarter of a wave. If you think about the shape of a wave, up and down and up, a little too far. So we're looking at just from middle to up. So from middle to up, we're seeing just a fourth of the wave shape, right? Fourth of the wavelength. Okay. Well, but that's just sort of the largest value of the wavelength this could have. Because if you went any larger than this, if you stretch this out any more, then you no longer have the antinode at the open end. And it simply won't resonate. It won't vibrate with a standing wave. Okay, so what else is possible, though? We got a little large there, but same length, same open end and closed end. What we see happen here, we have to have an antinode here, so it's open here, wide up. We have an antinode there, but we now have compressed things a little bit. We're bringing this in, and I guess I'm looking a little bit like this. Standing wave inside the column of air. And we have node, we have antinode, we have node, and we have antinode. And we have satisfied that rule about an antinode at the open end, no problem. What's going on here, though? What's the relationship between L and wavelength? How much of a complete wave are we seeing? Well, this kind of looks like it's missing in this column of air. We're missing this right here. So we would go down and down to the middle again. And so that's a fourth of the wave. We're missing the fourth, so we have 3/4 of the wave. So L is a distance equal to 3/4 of the wave. And let's one more example real quick here. Okay, same length, and well, now what? We compress this even more. We have a node there. We're going to have an antinode there. So we have to. This is going to be interesting. Watch the artistic skills just not appear. So kind of doing one of those, and back out, open. So those in. Look at that meeting at the middle. That's a node. It's an antinode. That's a node. That's an antinode, and back to the node. Just barely. Node, antinode, node, antinode, node, antinode. Okay. So, how is length related here? It looks like I've got if I do crest, trough to middle, there is one full wavelength plus that quarter of a wavelength. I've got 1 1/4 wavelengths. So 1 1/4 is 5/4 of a wavelength. Okay. Now, let's work out the same kind of deal about harmonics here with these columns of air. So when, I'm going to look at this first example here. When the wavelength is equal to, so this wavelength is equal to 4 times the length of the string. When that occurs, what's going on? There's this frequency. It's equal to, well, velocity divided by wavelength. Wavelength is 4L. All right, now, there's no simplification of that possible. That is our fundamental frequency in this column of air. And so now, how about the next one? When the wavelength is, this is going to be, wavelength is 4/3 of the length. 4/3 L. There's going to be this resonant frequency. It's resonating. There's a standing wave. Okay. And we have velocity divided by, our wavelength is 4/3 L. Okay, so this is equal to 3 times velocity over 4L. And you recognize that right here. So what we have is 3 times that fundamental frequency. Then what do we call this? What harmonic is this? Is this the second harmonic? No, it's actually the third harmonic, because it's 3 times the fundamental frequency here. There is no second harmonic for this column of air that is closed at one end. It just skips. It goes from 1 to 3. What do you think the next one's going to be? I think so too. It's going to be a 5. So when lambda, the wavelength, is equal to, so this final one. This final one here, okay, so I'm going to flip that. Wavelength will be 4/5 the length of the column of air. This frequency is equal to, okay, substitution, 4/5 L. So this is equal to 5 times V over 4L. There we go. 5 times that fundamental frequency. This, therefore, is the 5th harmonic, and there is no 4th harmonic with this column of air open at one end. Interesting. Let's make a general statement here. Generally. So, we have the, any harmonic of a column of air. Well, we've got it's equal to n times the fundamental frequency, which essentially is n times V over 4L. And this is when n is equal to 1 or 3 or 5, ... Because you simply don't get the even numbers. It's only the odd harmonics that show up. You cannot create a standing wave in a column of air that is closed at one end. That is the second harmonic or the 4th harmonic. However, what if you don't close that bottom end of that tube? All right, let's check it out. So, if it's open, you can probably imagine this. And you say, okay, well, we have a length from there to there. And now, since it's open at both ends, there's got to be an antinode at each end. And so the longest wavelength possible where this works is to have a single node in between them. And do that. Where the standing wave, there's a node, just shows this. So what is this? Well, this length represents, if I was going to complete a wave, I'd go from trough to crest, I have to go to the next trough out here. This is half of a wavelength. What's the next possibility? If it's open at both ends, I need an antinode at each end. So antinode at each end, and for that length it looks like I've completed, that's one full wave length. So L equals one wavelength. This is starting to look really familiar. I think I've done that before, and it turns out I've done it with the strings, right? I saw wavelength is twice the length, wavelength is length, wavelength 2/3 the length. I bet I would get the same 2/3 on the very next one. Let's see if we can get this going. This is going to be a little crowded, but essentially I will need a node in the center, and I will need a node about there, and I'm going to have to come through the middle, do that, and back there, and then there, and back open. Through the middle, antinode, through the middle of the node, there's an antinode, back to the middle, there's a node, and the antinode. Okay, yeah, so I got antinode at each end. And how about length relative to wavelength? I see from crest to crest, there's one wavelength, plus crest to trough, that's another half of a wavelength. So this is 1.5, or 3/2 of a wavelength. Is that what I saw? So I'm keep in mind, okay, back of the strings. Length is 3/2 of a wavelength. So wavelength is 2/3 of length. Yeah, it's identical. It's identical to a vibrating string that's fixed at both ends. Here it's open at both ends. So I can skip, for the sake of time on the video, I can skip a couple things and make a general statement here. Generally, there are harmonic frequencies here, where you get a standing wave. That's where the harmonics occur. And you have this n times the fundamental. But what is that? It's going to be n times speed of the wave divided by, so what is it? Well, with the strings, it was 2 times the length. And so I have that again. So there we go. This is a vibrating column of air that is open at both ends instead of closed at one end. And this is also where n could be 1 or 2. We see all the harmonics, the odd and the even here as well. So I wanted to run that by you about standing waves. It big time, huge application to music, but also elsewhere. Thank you for watching. I'll catch you next time.